So, let's talk about a huge challenge for anyone building with AI right now. How in the world do you create systems that can actually last when the technology itself feels like it's being completely reinvented like every single week?
Does this sound at all familiar? You're constantly chasing the latest model, the newest technique, that hot new paper that just dropped. It can feel like you're running on a treadmill that's just getting faster and faster and faster.
Well, I've got some good news for you. According to AI researcher Omar Khattab, that feeling of scrambling, it's not a sign you're falling behind. Nope. It's actually a sign that you're doing a good job. It means you're paying attention and you're trying to stay on top of what is an incredibly fast-moving field. But all this chaos brings up a really fundamental question. If everything is always changing, how can we possibly build anything that's meant to last? The answer, it turns out, lies in grappling with a famous and, kind of intimidating concept from the world of AI. It's called the bitter lesson. It comes from a short but really powerful essay by the reinforcement learning pioneer Rich Sutton. And it's an idea that's so influential that sooner or later, every AI engineer has to really wrestle with it. So what is this lesson? Well, at its core, Sutton argues that over 70 years of AI research, one thing has proven true again and again. Simple general methods that can leverage just massive amounts of computation will always, eventually, outperform the complex systems we build with our specific human domain knowledge. The bitter part is the realization that our clever, handcrafted solutions often just get in the way. And, that leads to a pretty terrifying question for all of us. If our human ingenuity, our expertise, is actually a problem to be overcome, then what is the point of AI engineering? Are we just wasting our time? The answer is a resounding no. And the reason why comes down to this really crucial distinction that often gets missed in this debate. We have to separate two very, very different goals. Okay, here's where it all clicks. The bitter lesson is really about the quest for artificial general intelligence, AGI. The goal of a machine that can learn absolutely anything. But that's a researcher's goal, not an engineer's. AI engineering has a totally different mission, building reliable, predictable, and controllable software to solve a specific problem. They're just two fundamentally different games. As Khattab puts it so well, we already have billions of general intelligences on the planet. They're called humans. And humans are, by our very nature, not always reliable or controllable. We build software precisely because we need systems we can count on. We actually build software to carefully subtract agency and intelligence in just the right places, to create something robust. So if human knowledge itself isn't the enemy, what is? The problem isn't using our brains. It's how and when we use them. And this reframes the bitter lesson into something that's actually much more familiar to us engineers. And here's the key insight, the bitter lesson. It's not some strange new AI concept. It's really just AI's version of a timeless software engineering mantra. Premature optimization is the root of all evil. Both are warning against the exact same thing, hard-coding clever solutions way too early. Take this famous, or maybe infamous, piece of C code. It's a legend in programming circles for being a super clever, super fast way to calculate an inverse square root. But it's also a perfect example of this problem. It works by using these bit-level hacks that are tied to one specific type of hardware. In other words, it's fast, but it is incredibly brittle. This is exactly what premature optimization is. You're committing to a solution at a much lower level of abstraction than you can really justify. You're building on foundations, like a specific piece of hardware or a specific AI model, that are almost guaranteed to change. You're building your house on sand, and it's just asking for trouble. So what's the modern equivalent of that brittle C code? In our age of LLMs, what is the single biggest form of premature optimization? Well, according to Khattab, the answer is hiding in plain sight. It's the prompt itself. Think about it. A single, long, complicated prompt is the modern-day version of that messy C code. It just tangles everything together into one big string. The fundamental task you're trying to solve, a bunch of random tricks such as happen to work for one specific model, the inference strategy like think step by step, and even formatting instructions like spit out the answer in JSON. It's a tightly coupled mess. So, if these giant over-engineered prompts are a trap, how do we get out? How do we build systems that can actually evolve with the technology instead of breaking every single time a new model comes out? The answer is another one of those timeless engineering principles: separation of concerns. Our job is to untangle that mess. We need to separate the fundamental logic of our application from the fleeting details of how we get one particular AI model to execute it today.
And in practice, this really just breaks down into a simple two-step process. First, invest your energy in the core durable assets of your application. And second, architect your system to decouple that core logic from all the swappable parts, like the specific model you're using today or a particular prompt tuning trick.
So what are those durable assets? What are your safest bets to invest in? Well, there are three. First, the essential specifications and signatures, clearly defining what each part of your system should do. Second, the control flow and tools. That's the unique logic and the plumbing of your application. And third, your evaluation data, the ground truth that tells you if your system is actually working, no matter which model is running underneath.
And this really leaves us with the big takeaway. Models are going to get better, algorithms will get faster, hardware will get more powerful, but they are never going to read your mind to figure out what you're actually trying to build. Your job as an engineer, defining the spec, designing the system, and proving that it works, is more crucial than ever. The lesson isn't that engineering is pointless. It's that we have to engineer at the right level of abstraction. So the only question left is, are you building for today's model, or are you architecting for every model that's yet to come?